So I strongly suggest taking a look at the beginning of this video and then pausing it and trying to do the things that I'm going to walk through before you watch me explain it. This is essentially putting everything together that we've seen in this entire chapter, and so these serve as great practice problems, review problems, and you're not going to necessarily have to do all of these different things when you do this homework in WebAssign. You're going to notice that sometimes in WebAssign all you need to know is a certain aspect of a function, and then you're going to be able to match a function up with a graph and things like that. But we're going to approach this as a review, and we're going to look at every single aspect of a function from an algebraic or analytical perspective. So we're going to get the intercepts. We'll start there, and then after we do the intercepts, we'll find the asymptotes. We'll do the first derivative analysis, get the relative extrema. We'll know when the function's going up or down. We'll do the second derivative analysis, get points of inflection, and know when the concavity is changing and when it's concave up, concave down, and then we'll sketch the graph. So here we go, intercepts. I am going to do this. I'm going to say let's plug in 0 for x, solve for y, and then plug in 0 for y and solve for x. And if you plug in 0 for x, you end up just getting 0 divided by -4, so that's going to be 0. And if you plug in 0 for y, you're going to get 0 equals x divided by x squared minus 4. But we know that a fraction is equal to 0 when the numerator is 0. So you actually end up getting the exact same intercept. So we don't even need this. We don't need to write it 2 different times. So there's one intercept here, and that intercept is 0, 0. Okay, let's go on to asymptotes. So now the asymptotes can be found using rules for asymptotes, or remember what we just learned in the last section was also a strategy for finding asymptotes. And so you could employ those ideas. You can say limit as x goes to infinity of x over x squared minus 4. And then you can also do the limit as x goes to negative infinity of x over x squared minus 4. Remember, because there's the potential for up to a couple horizontal asymptotes. And if we use the rules for horizontal asymptotes, since this degree in the numerator is smaller than that in the denominator, then we know that the horizontal asymptote is going to be 0. You could also go through the strategy where we would have divided every term by x squared, and you would have come to this conclusion that way. But this tells me that my horizontal asymptote for this graph is going to be y equals 0. Okay, our vertical asymptote, this goes back to what we did actually earlier in the class. Our vertical asymptote is the zeros, or are the zeros of the denominator. And so if you just set x squared minus 4 equal to 0, and you solve that, you're going to get x equals plus or minus 2. So we have 3 asymptotes here. We've got a horizontal, 2 vertical, and we've also got an intercept at this point. So now let's do some calculus. Let's do our first derivative analysis and find when our function's increasing, decreasing, relative extrema, relative maxes, relative mins, all that. So if I'm going to do my first derivative analysis, then I have to do my first derivative. So first derivative is f prime of x equals, looks like I need to do the quotient rule, right? I've got a fraction with functions of x in the numerator and denominator, so it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, and that's all over the bottom squared. So my cleaned up derivative is going to be, that's an x squared right there, x squared minus 4 times 1 minus 2x squared. So it looks like it's going to be negative x squared minus 4 all over x squared minus 4 squared. And even though it looks like something might cancel there, there is actually no cancellation whatsoever. Yeah, because if you factored out a -1, you'd have an x squared plus 4. So there's no canceling. So what we do when we do a first derivative analysis is we create this f prime number line. We label it f prime. And we need to enter on this number line a couple of things. Where is the first derivative equal to 0? And then where is the first derivative undefined? Now the first derivative is equal to 0 when the numerator of the fraction is equal to 0. And so you could try setting negative x squared minus 4 equal to 0. But what you're going to find is you're going to get x squared equals negative 4, and there's no x value that you can square and get negative 4. So there's never a place where the numerator is equal to 0. So this first derivative is never equal to 0, but you can look at the denominator and probably tell me the couple of x values when this derivative is undefined. And that would be at negative 2 and positive 2. Then I'm going to take a representative value from each one of these intervals and I'm going to substitute into the derivative. The easiest value to always substitute is probably 0. So if I plug 0 in, you can see that my numerator is going to be negative, my denominator is going to be squared, so my denominator is going to be positive, and so this is going to be negative. Now, actually, if you think about it, isn't your numerator always going to be negative? Because no matter what you plug in for x, when you square it and then negate that and then subtract 4, it'll always give you a negative number. So the numerator is always going to be negative, and the denominator, since you're squaring, is always going to be positive. So that means everywhere along this f prime number line, our function, or our first derivative is going to be negative. Okay, so there's our first derivative analysis. And we could say from this, you could say that f is decreasing. Gosh, f is decreasing the whole time, I think. It looks like f is decreasing from negative infinity to negative 2, from negative 2 to 2, and then also from 2 to infinity. And we can also say that there's no relative extrema. There is not a single relative max or relative min in here because we need the first derivative number line to change sign in order for that to happen. On to the second derivative analysis now. So you could see if my first derivative is negative x squared minus 4 over x squared minus 4 squared, I need to do the quotient rule again. So let's just come down here a little bit where I have some more space, because I think I'm going to have a lot more algebra this time. And this is the unfortunate thing that we sometimes run into when we're doing these second derivative analyses. So my second derivative is going to be, it's going to be equal to the bottom times the derivative of the top, so that would be times a negative 2x, minus the top times the derivative of the bottom. You have to use chain rule to do the derivative of the bottom, so that's going to be 2 times x squared minus 4 to the first, but then multiplied by the derivative of the inside, 2x. So the derivative of the bottom is 2 times x squared minus 4 to the first, but then multiplied by the derivative of the inside. And this is going to be all over the bottom squared, so all over x squared minus 4 to the fourth. So this is a lot of algebra, but we can do it. So what I'm going to do here is give myself a little bit more space and just start simplifying. So we have, let's see, we've got a couple big chunks here. So you've got this big chunk, and then you've got this big chunk right here. And so what I'm going to do is clean that up a little bit. Get rid of that one. So yeah, we've got these two big chunks, and we need to look for the greatest common factor in those chunks. I think that's going to be a really good way to do this. So you see this x squared minus 4 squared, and I also see an x squared minus 4 here. So I'm going to pull out an x squared minus 4 to start, and then I'm also going to pull out a negative 2x, because I've got a negative 2x here, and I've got a 2x here with this negative. So if I take this negative with that 2x, then I can take a negative 2x out from both this chunk and then this second chunk. And so this would now become a plus symbol. And so be careful. It was minus at first, but I'm pulling a negative 2x out, and so it becomes positive. And so then this becomes, if we're going to pull that out, we have to say what remains in the first chunk? Well, if you take an x squared minus 4 out and a negative 2x factor out, then you're left with another x squared minus 4. And then we say plus, here we've taken an x squared minus 4 factor out as well as the 2x, and so we have an additional 2 times negative x squared minus 4. And this is all over x squared minus 4 to the 4th. So if I simplify that a little bit more, I get x squared minus 4 times a negative 2x times, you're going to see that x squared minus 4 plus 2 times negative x squared minus 4 becomes negative x squared, because you have a 1x squared and a negative 2x squared. You have minus 4 minus 8, so it looks to me like it's negative x squared minus 12. And this is all over x squared minus 4 to the 4th. So I like simplifying this as, let's see, I've got an x squared minus 4 up top. I can cancel it with 1 on the bottom. So I like simplifying this as negative 2x times negative x squared minus 12 all over x squared minus 4 cubed. Wow, okay. So let's go to our second derivative number line. Don't worry, you're not going to have to do anything quite like that in the homework. I'm not going to test you on anything like that either. So the second derivative number line is going to look like this. And again, we always label that number line. And we need to find the places where the second derivative is equal to 0 and where the second derivative is undefined. Now remember, a fraction is equal to 0 when the numerator is 0. So that's when negative 2x equals 0, or when this piece is equal to 0. But this piece is never going to be equal to 0. So we're only going to get x equals 0 from our numerator, and then we get x equals plus or minus 2 again from that denominator, because that's where the second derivative would be undefined. Now, let's make some substitutions into this second derivative, which is right here. And if I make some substitutions in, this is always going to be negative, but then this is going to be negative only when x is positive, and it's all going to change depending on what interval you're using a value from. You can take a representative value like 1 and you end up with negative 2 times a negative, so that would be positive divided by 1 minus 4, that would be a negative cube, that would be negative, so a positive divided by negative would be negative. And you could take some other representative values, and what you would see is this. It's actually going to go like this. I'm just going to kind of tell you right now, but you can kind of do that on your own. And this tells us when our function is concave up, when it's concave down. And so we could say that f is concave down on the intervals from negative infinity to negative 2, as well as the interval from 0 to 2. And then f is concave up on the intervals from negative 2 to 0 and 2 to infinity. So we've got all of this info using everything we've done for this entire from this entire chapter. So we've got these intercepts, we've got the asymptotes, and what we can do is we can sketch a graph beginning with those intercepts and asymptotes, and then incorporate the info from the first derivative analysis and the second derivative analysis. And it actually is a graph that we can get rather quickly. So I think maybe I'll sketch it just on this right side right here. And so when I create my graph, I'm going to just keep it really simple with how I'm labeling this graph. And so I'm going to go 1 and 2 because we knew we had asymptotes at plus or minus 2, so negative 1, negative 2, and then I'm not even going to label anything on the vertical axis right now. And so we've got an intercept at 0, 0. We've got asymptotes right here, as well as right here. We also have a horizontal asymptote at y equals 0, and so that's right here. So I've got a horizontal asymptote right along my x-axis. And the asymptotes themselves can actually dictate the behavior of what this is going to look like. I mean, you know, if you've got asymptotes here and here, that this section of the graph, it's either going to have to look like this, or it's going to have to look like this. But what was our first derivative? Less than -2. First derivative was negative. So that means our function is decreasing. And therefore, you could reason that it's going to have to look like this. And so we almost know the concavity without even looking at our concavity analysis. But what do you know? When you check the concavity, you can see that that second derivative we determined was going to be negative, so our function was going to be concave down less than -2. It's also fairly easy to sketch the graph greater than -2 because, again, you know it's either going to look like this in this upper quadrant or it's going to look like this. And since we know that our function's decreasing again, it's going to have to be this upper quadrant. And so when we look at our second derivative number line, our second derivative should be positive when x is greater than 2, and it is. And so that checks out. So the only other thing we have to do to sketch this graph is figure out what's going on in the middle. But we're decreasing the whole time between -2 and 2. So you can't start here and rise. So you're probably going to start up here, and here you do have to consider the concavity. And if you look at that second derivative number line that we have filled out between -2 and 2, it goes from concave up to concave down. Okay, so I'm sketching this where it's going to go concave up to concave down. And sometimes I kind of accentuate it a little bit more after the fact, because I know that the concavity is in fact changing at 0, 0. So I didn't say it before, but 0, 0 is the only point of inflection. When we looked at that second derivative number line, maybe you were thinking this was going to be a point of inflection and this was because the concavity is changing there. But for it to be a point of inflection, it's got to be a point on the graph. And so -2 and 2 were not technically points on the graph. But this is it. This is how you sketch a graph. This is how you put it all together. And in the next video, I'll do one more of these examples.